get some color into this. Getting started with the IBM Q experience. Also the same author. So let's take a look at this. I haven't really read through, but I see that there's a link to the IBM Q experience. I'll actually explore the experience website in another video. So I'm just going to focus here on reading through the article and seeing whether there's something interesting to learn, or it's just just about the size. How now that you can use kind of computer for the first time, this guide will show you how to set up a simple experiment. Oh, interesting. So the first puzzle in the Hello Quantum game. To go to IBM experience, go here, and then you should get something like that. So this looks like that's basically where you compose your circuits, where you build your quantum computing algorithms or circuits. The compose is where you run your quantum programs. Good. By default, it starts you off with 5 qubits of a real quantum processor known as IBM QX4, but let's instead focus on something a bit simpler. Just 2 qubits. Okay, so to this, click on the new button. The next job is to choose whether you work the real devices. So that's basically explaining you how the site works, how you can set up the composer. Okay, so you have different quantum computers, and you can have a custom one, which is probably a simulator. So here they basically, okay, number of qubits 2, number of qubits 2, and those are classical registers. So this is where you're going to probably write the measurements, because it's classical bits, I assume, and those are the quantum bits. Okay, so you've got that, and here you can see gates. Okay, let's see. The boxes represent different operations you can do with the gates. And we've seen the X, we've seen the Hadamard, we also see the Z, but I don't see here any control Z or anything. I see the control knot. The boxes, I think you, like, based on what I've been doing already, you can probably already now, because I don't know when the article was written, but I think you can already now create your own gates based on combinations of other gates. Maybe there are more types. All we need to do is drag and drop them into the lines. So here we have an X in here. Okay, that's the job, and that's the job done. Okay, let's see. All right, the first puzzle of Hella Quantum looks like the image below. Okay, so that's the first puzzle, where we have basically we have a on and an off beat. So that's a 1 and a 0. And this, we know now that this means they disagree, right? So the grid in here is basically telling you whether those pairs of qubits agree or disagree, or measurements, they agree or disagree. Okay. And that's entanglement, by the way, entanglement. The way we get the outputs for the bottom circle is using the measurement gate. Yeah, the measurement, the basic measurement. Okay, so look at the bottom circle. Both we drag the measurement gate over both lines. When we do this, it will ask what name you give to the resulting beat. Just press OK. Okay. Once both gates are in place, it's time to get the results. Here is missing the gate. Okay, but I guess that's what. Okay, so that's one here, and then I assume there's the other ones here. So you haven't just signed in yet. Okay, so here's now sign up, whatever. And then these are the results. Okay, so you've only put one. You've put the next gate, and so you measure like 1, 0, 100%, so all the time. Okay. Yeah, that seems a fairly smooth introduction, having visited already all the other concepts. So make sure you check out the other videos, because the more intuition I build, the quicker I'm gonna jump over certain topics. I'm gonna try to link the videos in a way that you can also follow that as well if you want. Yeah, and basically that's okay. Now level 1, puzzle 1. So okay, and that gives you the output for the top circles. Good. Yeah, which basically it's of equal probability. While we see that it's not always purely equal, but that's because it's never perfect, right? It's just that the more measurements you do, the more equal those probabilities will look like. It's roughly 25. It's roughly 25%. Yeah, it's almost certainly. Find different numbers because for every execution it's going to be a bit different. Let's do another example. Level 4 puzzle. That's an interesting one. Level 4 puzzle. I haven't gotten to level 4 yet. And I'm guessing here you're going to have to use the Control Z gate, which I still don't fully understand completely. But let's see what they say. So this is what I do. This is to first make the target gate and then work backwards to the initial state. Okay. I guess for the purpose of demonstration. Yeah. The target state has a black top circle for the left qubit and a white top circle for the right qubit. If you have played Hello Quantum and read the Learn More section or this article, you probably hopefully be clear that this can be set up as the image below. So yeah, okay, so they're both Hadamard, and then you flip one to the minus state. So this is the plus state and this is the minus state. And that's what you have here, so to say. The plus state and the minus state. Yeah. Oh, sorry, because we're doing this first. So you have the minus state and the plus state is here. Okay. And then basically now we have to work out. Now they want to work. He wants to work out how to get that state. And I see that's already doing something weird here. So we need is Control Z, but we don't have that one. But you can click on the advanced checkbox. That's what I thought, and then scroll down. You'll find the Control Z under subroutines. Here, Control Z, and this Control Y. Control Y. We don't know all that stuff yet, but there's Control Z. The subroutine gates are gates you can make yourself, and the Control Z is provided as an example. Cool, because it doesn't get its own custom-made symbol. Instead, it just gets a generic symbol for subroutines. This AB thing. If you want to run jobs on a real device, you won't be able to use any subroutine. But don't worry, there's still a way to get the CZ in a real device. Okay, so I guess that's just a limitation of the way the quantum computer works currently, the state of development. And there's a way you can do Control Z. It's known as the C naught, so you can trick that. One of the main differences between the C naught and the CZ is that it's not symmetric, so we have to be careful about which way around we point it. The qubit that gets the little dot will play a different role as the control. So I guess I'm guessing this article is the one that I made already a video about, where it tried to explain how the CZ works. Okay, so here's another way you implement the Control Z. Probably not interested in that, in knowing that detail. So the X might be applied rather than a Z. And since we know, so to turn a C naught into a CZ, all you need to do is a Hadamard gate, then a control node, and then a Hadamard gate. Why? Why is that? So if you're doing a Hadamard gate, you're gonna get into the plus state. Then you do a control node, and you will. And that's it. So maybe that's also a key to understanding a bit more how the Control Z works. But if you have a Control Z, if you do a Hadamard gate, a Hadamard first, and then you do a control not. So what's happening here? Let's see. Let's see. Let's open the notebook, the notepad, like we did last time. Maybe that helps. So we start with 0, 0. So we apply a Hadamard gate to the qubit 1. That turns our state into 0, 0 plus 1, 0. Now we apply the control not from 0 to 1, from 0 to 1, right? So this stays like that. That's okay. From 0, yeah, and that stays like that. Kind of weird. In the case of 0, 0, okay. And then you apply the Hadamard again, which basically gives you with this plus this and this minus this. So you see that those two cancel. So at the end of the day, what you end up with is just this. So you're back to 0, 0. Whereas if you apply the same to a 0, 1, right? Then you're gonna have let's just copy that. So and then you've got a 0, 1 plus 1, 1. And if you now do control not, then you have a 1, 1 plus 0, 1. And if you now do a Hadamard, then you've got a minus 1, 1 plus 0, 1 plus 0, 1 plus 1, 1. So basically the 1, 1s go away and you end up with 0, 1. Stays the same. Is it the way that I'm reasoning that is not correct? Because you want to end up with a minus state, right? You want to end up with a minus state after control. I mean, no. You only want to, okay. You end up with a minus state if you start with a plus state. Okay. Of course. Which basically, that means if we start with a plus state, which is this plus this, is it? No. 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 You see again, it's because it's a trick of 2 qubits, right? It makes it a bit more difficult to reason. So the plus state is this, right? But let's assume that the qubit 0 is 1, so the actual gate happens, and now we have that. So if we apply Hadamard to that whole thing, then you've got basically 0, 1 plus 1, 1, and you've got another 0, 1 minus 1, 1. And if you apply control X between the 0 and the 1, then you've got a 1, 1, you've got a 0, 1, you've got a 1, 0, and you've got a minus 0, 1. So and that basically you can cancel out the 0, 1, so that ends with 1, 1 plus 1, 0, which means if you do a Hadamard 1, you end up with a 0, 1 minus 1, 1 plus uh, 0, 0 minus 1, 1. Good, and those things, and the 1, 1s go away, so you end up with 0, 1. Mm. Hmm. End up with 0, 1 plus 0, 0, which basically means that, what does this mean? I don't know. Maybe I just made a mistake. Um, I'll take that as again part of the challenge of how the control set works. Good. Um, and I'm gonna summarize all that in a video. So the control set is giving me trouble. I see, understand the control set is giving me trouble, and how does this you know how does this basically equal the control set, and this also equals the control set. And I don't want to go. I want to prove that at an intuitive level, so I understand what the control set means. Um, okay, perfect. And that's it. So here I have the levels. Okay, cool. So next up is control Z. Control Z, I gotta figure out what the hell you are. What is the explanation? Okay, maybe a good way to go about it is actually I can probably play with that, and I would try to understand what are the effects of the control set. Maybe that's gonna be the right tooling to figure this out. Cool, perfect.